Now I want to share the important questions list. Ma, you take it.
Okay, ma'am.
Screenshot.
Okay, ma'am.
Okay. So repeated questions is there, man. All universities, Mahatma Gandhi universities, Usmania University, Palamuru, and second semester papers and matter. So repeated questions also there. We sort out important in that all. Okay. Coefficient of basis of kinetic theory of gases. Diffusion, transport phenomena is there. No, first class we discussed that. Next, statistical equilibrium, difference between classical quantum statistics, Planck's radiation. Next, entropy, explain the Maxwell distribution law. Entropy temperature diagram, obtain the equation 1 minus T2 by T1 from TS diagram. Thermodynamic potentials and Maxwell equations are very, very important. Next, adiabatic demagnetization, principle used to produce low temperature physics. Next, Wien's displacement law, pyrometer, construction and working of pyrometer. Any three or two papers you should be perfect, then you get easily good marks only. Okay. Next. Okay, ma, in this also same. What it is transport phenomena. Above paper we are having.
మ్యామ్ ఈ 3 మోడల్ పేపర్స్లో ఏ రో మోడల్ పేపర్స్ కరెక్ట్ ప్రిపేర్ ఉన్నా కరెక్ట్ స్కోర్ చేయొచ్చు అంటున్నారు 3 మోడల్ పేపర్స్. హలో,
చెప్పండి అమ్మా.
ఈ 3 పేపర్స్ లో ఏ 2 పేపర్స్ నుంచి చదువుకోమంటున్నారా?
అవునమ్మా, అవును.
ఈ త్రీ మోడల్ పేపర్స్ లో. ఓకే.
రిపీటెడ్ క్వశ్చన్స్ కూడా కొన్ని ఉంటాయి. ఇప్పుడు ఇక్కడ దీంట్లో ఏం చెప్పామన్నమా, ట్రాన్స్పోర్ట్ ఫినామినా ఉంది, విస్కాసిటీ ఆఫ్ ఎ గ్యాస్ ఆన్ ద బేసిస్ ఆఫ్ కైనెటిక్ థియరీ. ఇంత ముందు పేపర్ ఏమో డిఫ్యూజన్ వచ్చింది, ఇక్కడ విస్కాసిటీ ఇచ్చాము. ఈ అండ్ కండక్షన్ 3 కలిపే కదా ట్రాన్స్పోర్ట్ ఫినామినా. అటెండ్ అయ్యారా క్లాసెస్ ఇంత ముందు? ఎంట్రోఫీ, నెక్స్ట్ వాట్ ఈస్ ద ఫిజికల్ కాన్సెప్ట్ ఆఫ్ ఎంట్రోఫీ, రైట్ ఏ షార్ట్ నోట్ ఆన్ ఎంట్రోఫీ చేంజ్ ఇన్ రివర్సిబుల్ అనేది ఇక్కడ క్వశ్చన్ అనమాట. 15 ఎస్ఏ క్వశ్చన్స్ ఇవన్నీ.
అటెండ్ డౌన్ క్లాసెస్ యూట్యూబ్ లో పెట్టారు మా, అది తర్వాత చూసి క్యాచ్ అప్ అవ్వచ్చు.
ఓకే. నెక్స్ట్ జౌల్ కెల్విన్ ఎఫెక్ట్, మాక్స్వెల్స్ థర్మోడైనమిక్ రిలేషన్స్, జౌల్ కెల్విన్ ఎఫెక్ట్, మాక్స్వెల్ థర్మోడైనమిక్ రిలేషన్స్. నెక్స్ట్ వాట్ ఈస్ రీజనరేటివ్ కూలింగ్, లిక్విఫైయింగ్ ఎయిర్. నెక్స్ట్ ఫ్లాంక్స్ ఫార్ములా ఫర్ ద డిస్ట్రిబ్యూషన్ ఆఫ్ ఎనర్జీ ఇన్ బ్లాక్ బాడీ రేడియేషన్. టుడే క్లాస్ విల్ కంప్లీట్ దట్. ఫ్లాంక్స్ రేడియేషన్ లా, అండ్ హౌ టు మెజర్ ద సోలార్ కాన్స్టెంట్ యూజింగ్ experimental pyrometers, measuring of radiation. Next Maxwell distribution law and molecules, first lesson that, and Maxwell velocity distribution law. Next Fermi Dirac Fermi energy. ఇవన్నీ ఇంపార్టెంట్ అని 2 పేపర్స్ సెండెడ్ ఆల్రెడీ. ఇది టేబుల్ now this one. Postulates of kinetic, almost all papers. First kinetic theory of gases only. Next ratio of specific heats in some, in that is relation. Next one, what are Maxwell relations, explain the 2 specific heats of gas, obtain the expression for the difference between 2 molar specific heat. Next, distinguish between Joule-Thomson cooling and adiabatic cooling. Next, helium, how can be liquefied. Next, Planck's hypothesis, radiation law, Planck's radiation law. Next, Rayleigh-Jeans law and Wien's displacement law. Pyrometer and disappearing filament optical pyrometer. Next, last unit వచ్చేసి Maxwell distribution law of molecular speed in an ideal gas. Next, Bose-Einstein distribution law, mathematically apply it to photon gas to obtain an energy distribution. జౌల్ కెల్విన్ ఎఫెక్ట్ రిలేటెడ్ ఒకటి ఉంటుంది, ఫ్లాంక్స్ రేడియేషన్ లా కంపల్సరీ ఉంటుంది. నెక్స్ట్ కైనెటిక్ థియరీ ఆఫ్ గ్యాసెస్ లో విస్కాసిటీ అండ్ ట్రాన్స్పోర్ట్ ఫినామినా, సోలార్ డిటర్మైన్డ్, బోస్-ఐన్స్టీన్ డిస్ట్రిబ్యూషన్. రిపీటెడ్ క్వశ్చన్స్ ఉంటాయమ్మా, ఏవి రిపీటెడ్ అవుతున్నాయో ఫస్ట్ యూ షుడ్ బి ఫోకస్ ఆన్ దట్ క్వశ్చన్స్. పేపర్ మోడల్ కొన్ని షార్ట్ ఆన్సర్స్ ఎక్కువ ఉంటాయి, కొన్ని ఏమో 12 మార్క్స్ ఇచ్చారమ్మా. యూనివర్సిటీని బట్టి డిఫరెంట్ ఉంటుంది అక్కడ. షార్ట్ ఆన్సర్స్ ఏంటి, లాంగ్ ఆన్సర్స్ ఏంటి, ఫస్ట్ గెట్ ద ఐడియా, దెన్ యూ ప్రిపేర్ ఎనీ 6 or 5 long answers and minimum 12 short answers you should prepare. Okay.
మేము ఒకసారి జూమ్ అవుట్ చేస్తారా, స్క్రీన్ షాట్ తీసుకుంటాం. ఓకే.
ఫైవ్ సిక్స్ యూనివర్సిటీ మోడల్ పేపర్స్ సెండ్ చేశాను. ఇప్పుడు వీటిలో ఎనీ 3 పర్ఫెక్ట్ నేర్చుకున్నా సరిపోతుంది. వన్స్ యూ చెక్ ఇట్ ఆల్ ద పేపర్స్ విచ్ ఆర్ మెయిన్ maximum long answers, which are short answers, then you can prepare like that. When you are having exams, is there any schedule given?
Next month 17th, ma'am.
Given a date?
Next month 17th.
April 17th, okay. Okay, yesterday class we have completed adiabatic demagnetization. That is also very important question. Vapor compression mission completed. We prepare the 2 questions. Next, quantum theory of radiation. We will start. Quantum theory of radiation also. What is conduction, convection, and radiation? Thermal radiation, emissive power, Boltzmann's law, and Ferris black body, absorptive power, spectral power, distribution of energy in spectrum of black body, Wien's displacement law, Rayleigh's law, Planck's law. That will complete today class. Okay. So all units important questions you should cover. Don't prepare only 2 units, means remaining 2 units you are leaving the questions. So no, don't prepare like that. In this model paper you check out in which one unit, one essay question compulsory. Choice more means 2 questions compulsory. So that you prepare like that. Long answers you should be prepare all the units. Next, quantum theory of radiation. So in this quantum theory of radiation, so what is introduction for this lesson? These are 3 types of transmission of heat takes place from one place to other. The one place to other or the one point to other. These are conduction, convection, and radiation. So what is mean by conduction? What is mean by convection and radiation? Conduction means that the transmission of heat takes place from one point to other point without motion of particle. The transmission of heat takes place from one point to other point without motion of particles is known as conduction. In this mode of heat transmission, particles, molecules transfer heat by collisions. Conduction means there are 3 types of modes of transmission of heat from one place to other place or one region to other region. First one is conduction. What is mean by conduction? The transmission of heat takes place from one point to other point without motion of particles is known as conduction. Next one, in this mode of heat transmission, particles, molecules transfer heat by collisions. Particles or molecules transfer heat by collisions, but there is no actual moment of particles and molecules. This mode of heat transmission takes place in solids, means conduction takes place in solids. Next one, convection. Convection means the transmission of heat takes place from one place to the other place with the motion of particles, or molecules. With the motion of particles or molecules is known as convection. In this mode of heat transmission, molecules, particles transfer heat by move from one place to other place. Okay, in this mode of transmission, how it is transfer? Move from one place to other place by molecules only. This mode of heat transmission takes place in fluids. Fluids is moving like heat in the form of convection. Next one, radiation. What is radiation? The process of heat transfer. From a body by virtue of its temperature. The process of heat transfer from a body by virtue of its temperature without the involvement of the intervening of medium is known as radiation. Any medium is not required, ma. Direct sun radiation. In this mode of heat transmission, the radiant energy, in this mode of heat transmission, the radiant energy is transported. In this mode of heat transmission, the radiant energy is transported. The radiant energy is transported by electromagnetic waves. The radiant energy is transported by electromagnetic waves. Next, in addition to emitting radiation, the surface of a body has the capacity for absorbing all or part of the radiation emitted by surrounding surfaces, or all or part of the radiation emitted by surrounding surfaces and falling on it. That is the radiation. Next, thermal radiation. The radiation emitted by a body by virtue of its temperature. The radiation emitted by a body by virtue of its temperature is called thermal radiation. Emission characteristics. Here emissive power means total hemispherical emissive power, that is denoted by the letter E. What is E? What is E? E is equal to W by M square. Emissive power of a black surface is denoted by EB. So that E is equal to W by M square. Emissive power of a black surface is denoted by EB. Next, Stefan-Boltzmann's law. The total amount of radiant energy emitted by a black surface or black body per second per unit area. The total amount of radiant energy emitted by a black surface or black body per second per unit area is directly proportional to the fourth power of its absolute temperature. Therefore, EB is directly proportional to lambda T power 4. If you are removing directly proportional, we are taken as constant. Therefore, EB is equal to sigma T power 4. EB is equal to sigma T power 4. Here sigma is Stefan's constant and sigma is equal to 5.67 into 10 power minus 8 watt by meter square, 10 power minus 8 watt by meter square hyphen Kelvin power 4. So in general, the rate at which the rate at which the leaves an object is given by dq by dt is equal to E sigma into AT power 4. dq by dt is equal to E sigma AT power 4 for an object T1 and surroundings T2. Therefore, dq by dt is equal to E sigma into E sigma A into T1 power 4, E sigma A into T1 power 4 minus T2 power 4, E sigma A into T1 power 4 minus T2 power 4. Next, emissivity, that is the Stefan's-Boltzmann's constant. Stefan's-Boltzmann's law is EB is equal to sigma T power 4. What is EP means? It is the emissive power. So the total amount of radiant energy emitted by a black surface. The total amount of radiant energy is emitted by a black surface or black body per second per unit area. Is directly proportional to the fourth power of its absolute temperature. EB is directly proportional to T power 4. Removing that means sigma T power 4. From that, we are getting the rate at which the energy levels of the object is given is dq by dt, that equal to E sigma AT power 4. Then finally, we are getting E sigma A into T1 power 4 minus T2 power 4 from the object to surroundings, which is Stefan-Boltzmann's law. Next one, emissivity. What is mean by emissivity? It is denoted by the letter epsilon. The ratio of emissive power of real subspace to the emissive power of black body. The ratio of emissive power of real surface to the emissive power of black body. Ratio of emissive power of real surface to the emissive power of black body or black surface at the same temperature. Emissive power of black body or black surface at the same temperature. Black surface at the same temperature is known as emissivity. It is denoted by E. E is equal to E by EB at the same temperature. Epsilon E is equal to E by EB. The range of emissivity is 0 less than or equal to, the range of emissivity is equal to 0 less than or equal to epsilon less than or equal to 1. Next, spectral emissive power. Spectral emissive power denoted by the letter E lambda. The rate of radiant flux. The rate of radiant flux emitted by unit surface area. The rate of radiant flux emitted by unit surface area of the body per unit wavelength range. Per unit wavelength range is known as emissive power. It is denoted by E lambda. It is denoted by E lambda. It is denoted by E lambda. Then what it is, E lambda is spectral emissive power. E lambda is equal to W by M square. E lambda is equal to dE by d lambda. Then dE is equal to E lambda d lambda. Small part dE means entire part E is equal to integral dE. Integral 0 to infinity dE means dE lambda d lambda. Then spectral emissive power E is equal to integral 0 to infinity E lambda d lambda. Next, spectral emissivity E lambda. The ratio of spectral emissive power of a real surface to the spectral emissive power of black body. The ratio of spectral emissive power of a real surface to the spectral emissive power of a black body or black surface is known as spectral emissivity. It is denoted by E lambda. Therefore, E lambda is equal to E lambda at the same temperature and same wavelength. At the same temperature and the same wavelength. The ratio of spectral emissive power of a real surface to the spectral emissive power of black body. Black surface is known as spectral emissivity. It is denoted by E lambda. Therefore, E lambda is equal to epsilon lambda is equal to E lambda by EB lambda at the same temperature and same wavelength. Next, absorptive power. The ratio of the radiant energy absorbed per second by unit surface area. Unit surface area of the body to the total energy. Unit surface area of the body to the total energy falling per second on the same area. Per second on the same area is known as absorptive power. It is denoted by A lambda. Therefore, in general, when the radiation falls on a surface, when the radiation falls on a surface, a part is absorbed and the rest is reflected. A part is absorbed and the rest is reflected. If the body is transparent, a part may also be transmitted. If the body is transparent, a path may also be transmitted. Therefore, the sum of reflectance, absorptance, and transmittance. The sum of reflectance, absorptance, and transmittance is numerically equal to 1. That is the total absorptive power. Next, we'll go for actual syllabus, that is black body and black body radiation. Next, what is black body and what is Ferri's black body? Distribution of energy in the spectrum of black body. Next one, black body means what, which allows all the incident radiation and internally absorbs all of it is called black body. And at the same time, it emits also. Okay, a black body is one that allows all incident radiation and internally absorbs all radiations and internally absorbs all of it. Next, a black body emits the maximum amount of radiation at a given temperature. Black body emits the maximum amount of radiation at a given temperature. Hence, black body is not only perfectly absorber. Black body is not only a perfectly absorber but also perfect radiator and emits radiant energy. The nature of radiation emitted by black body depends on its temperature. The nature of radiation emitted by black body depends on its temperature. There is no body perfectly in character. There is no body is perfectly in character black body. The nearest approach is lamp black or platinum black, acts as a perfect black body. So the perfectly black body is just an ideal concept. Perfect black body is an just ideal concept. Perfect black body is not there in universe. Nearest approachment of black body is lamp black or platinum black. For all practical purpose, a lamp black surface may be considered as a perfectly black body. Next one, Ferris black body. That construction is shown in figure. So here only one entrance is there, that is O position. Ferris black body is shown in figure. It consists of double wall conducting spheres. Consisting of double wall conducting spheres. The inner sphere is S2. The inner sphere is S2, which is coated by the lamp black. The outer sphere is S1, which is coated with nickel. There is space between S1 and S2 is vacuum, because to prevent loss of heat. By conduction. Black body contains small hole O. And conical projection P is shown in figure. And conical projection P as shown in figure. Now consider that the radiation of light coming from the sources. And incident on the hole O. It passes inside the enclosure. It incident from the O and passes inside the enclosure. The radiation suffers multiple reflections inside the enclosure. And is completely absorbed. If the radiation of light incident exactly opposite to the hole, the radiation by reflecting get outside the enclosure. Okay, it passes inside the enclosure. The radiation suffers multiple reflections inside the enclosure and is completely absorbed. If the radiation of light incident exactly opposite to the hole, therefore the radiation by reflecting get outside the enclosure. The radiation by reflection get outside the enclosure. We have avoided such problem with conical projection P. Hence, the hole act as black body. The particular hole act as a black body. If the enclosure is heated through a particular temperature, it emits the radiation. If the enclosure is heated through a particular temperature, it emits the radiation. It emits the radiation having all possible wavelengths. That is called black body. Next one, distribution of energy in the spectrum of black body. Here, what it is for different temperatures, different wavelengths, how it is giving that shown in curve. A graph is drawn between intensity of radiation E lambda and wavelength lambda at different temperatures. The curves so obtained as shown in figure. Okay, but the different temperatures for different wavelengths, how the curves are drawn, that was shown in figure. Black body is not only a perfect observer but also a perfect radiator. Black body is not only a perfect observer but also a perfect radiator and emits radiant energy. The nature of radiation emitted by black body depend on its temperature. The nature of radiation emitted by a black body depend on its temperature. The emission from a black body at any temperature is composed of radiation from all wavelengths. The emission from a black body at any temperature is composed of radiation from all wavelengths. At a given temperature, the intensity of radiation increases with increase in wavelength. And for a particular wavelength, its value is and particular wavelength, its value is maximum. Beyond of this wavelength increases, the intensity also decreases. Wavelength beyond that intensity of wavelength increases, the beyond of this wavelength increases, the intensity decreases. Okay, na? At a given temperature, at a given temperature, the intensity of radiation increases with increase in wavelength, and for a particular wavelength, its value is maximum, and particular wavelength, its value is maximum. Beyond this, if the wavelength increases, the intensity, beyond this, the wavelength increases, the intensity decreases. Next, the energy is not uniformly distributed. The energy is not uniformly distributed in the radiation spectrum of a hard body. In the radiation spectrum of a hard body at a given temperature, the energy is not uniformly distributed in the radiation spectrum of a hard body at a given temperature. Therefore, the wavelength at which maximum emission of energy takes place decreases with increase in temperature. The dotted line represents lambda m. The dotted line represents lambda m at various temperature. The dotted line represents lambda m at various temperature. It is called Wien's displacement law. The dotted line represents lambda m at various temperature. It is called Wien's displacement law. Therefore, lambda m into T is equal to constant. Lambda m into T is equal to constant. Next, area under different curves. Represents the total energy. Emitted for the complete spectrum. Total energy emitted for the complete spectrum at a particular temperature. This area becomes more and more with increase in the temperature of the body. Therefore, the total energy of radiation at any temperature emitted is found to be directly proportional to the fourth power of its temperature. Therefore, E is directly proportional to T power 4. E is directly proportional to T power 4. So that E is equal to integral 0 to infinity E lambda d lambda is equal to sigma T power 4. That is Stephen's law. Next one, Wien's displacement law. This is sometimes asking for VSQ, means short answer, sometimes asking for essay question also. Just first understand the definition, then we will derive the derivation. Wien's displacement law. The wavelength corresponding to the maximum energy, is inversely proportional to the absolute temperature. The wavelength corresponding to the maximum energy is inversely proportional to the maximum energy is inversely proportional to the absolute temperature, or the product of wavelength corresponding to maximum energy. Lambda m, and the absolute temperature is constant. Therefore, lambda m is directly proportional to 1 by T. Lambda m into T is equal to constant. Lambda m into T is equal to B, that equal to 0.2892 into 10 power minus 2. 0.2892 into 10 power minus 2 millikelvin, where B is Wien's constant, For that, consider a spherical enclosure with perfectly reflecting walls and capable of expansion radially outwards. For that, we can take the total internal energy U of radiation is given by capital U is equal to small uv. Now we are applying for continuation of that. I will give you take the screenshot and prepare that. Then we'll go for Planck's law. That is important. So this it is a Wien's displacement law. Okay, 1 by U is equal to UV, that we are substituting in first law of thermodynamics. dq is equal to du plus dw. dq is equal to 0. Today's last class, no, that's what a little bit fast, ma. dq is equal to 0, then substitute 0, then that du plus pdv. But we know that p is equal to 1/3 of u, ma. Substitute this to what it is 1 3 in equation 2. Then d of u, differentiation of uv plus 1/3 u into dv is equal to 0. Then u differentiation of uv means u into dv plus v into du is equal to 1/3 into u dv is equal to 0. Therefore, 4/3 u dv plus 1/3 u dv is equal to 4/3 u dv plus v du is equal to 0. Therefore, dividing by uv, then dividing by uv above equation, then what we have? 4/3 1 by v dv plus 1 by u du. On integrating this equation, we are getting 4/3 log e of v plus log e of u. That integral 1 by u du means log e of u that equal to 0. So next, what it is, it is a log m plus log n means log mn, and 4/3 takes as power. Then it is v power 4/3 into u is equal to constant. Now v power 4/3 in the place of u, you can take as Stephen's law, which is sigma t power 4. Therefore, v power 4/3 sigma v power 4/3 sigma t power 4 is equal to constant. What is V ma? Volume of the enclosure, which is 4/3 pi r cube whole power 4/3 into t power 4. Here cube gets cancelled. Then that will be constant, means what we are getting finally, RT is equal to constant. R into T is equal to constant, which is equation 4. This radiation field in the enclosure will undergo continuous reflections from the moving walls of the enclosure. Due to Doppler's effect, the wavelength will be changed. Due to Doppler's effect, the wavelength will be changed. Therefore, the change in wavelength can be calculated. Therefore, due to Doppler's effect, the wavelength will be changed. The change in wavelength can be calculated. Therefore, let OA be a ray of wavelength lambda. Let OA be a ray of wavelength lambda incident at an angle theta on the wall in position S1. AC is the reflected ray at B, and reflected ray, and AB is the refracted ray. In the duration of second reflection, the wall has moved a distance AMBT. Therefore, second reflection takes place in the position S2. Like that, we are calculating for the continuation of that. I will send you, ma'am. Up to this, it is a Wien's displacement. Further steps we are taken. Then in the place of d lambda, we are substituting 2 nu lambda by c cos theta. Then c by 2r cos theta. All we are substituting. Finally, we are getting lambda m into t is equal to constant, which is Wien's displacement law. Next, Planck's radiation law. I will share you Planck's radiation law. Prepare this also important. Okay, next after this pyrometism. After this, the pyrometers, Armstrong pyroheliometer, radiation pyrometers, Armstrong pyroheliometer, determination of solar constant. You prepare that after this topic. Planck's radiation law, solar constant of Armstrong pyroheliometer is important. So in this Rayleigh's law, means displacement law, and Planck's law. Now we will start the Planck's radiation law. This is over, no? Now I will begin. This one, Planck's radiation law. Okay, what it is, ma? The emission of radiation is due to vibration of charged particles in the body. The postulates of Planck's quantum theory. First postulates. What are the postulates developed by Planck that we discussed, ma? The emission of radiation is due to vibration of charged particles. The emission of radiation is due to vibration of charged particles in the body. Now we will discuss that a black body radiator contains simple harmonic oscillator. A black body radiator contains simple harmonic oscillator of all possible frequencies. A black body radiator contains simple harmonic oscillator. A black body radiator contains simple harmonic oscillator of all possible frequencies. The emitted radiation propagates in the form of waves. The emission is not continuous, but in discrete packets of energy. The emission is not continuous, but in the discrete packets of energy is called quanta. The emission is not continuous, but in discrete packets of energy is called quanta. The energy epsilon associated with each quantum, for a particular radiation of frequency is given by E is equal to h nu. In general, for an oscillator of frequency nu, the possible values of energy are given by E is equal to NH nu. This notes will compare with your textbook, then you prepare. Next, Planck's radiation. Up to this, it is postulates of Planck's law. Then Planck's radiation law. What it is? Let capital N be the total number of Planck's oscillator. Capital N be the total number of Planck's oscillators, and EB and capital EB capital E be their total energy. Then the average energy per Planck's oscillator E bar. The average energy per Planck's oscillator E bar is given by E bar is equal to E by N. E bar is equal to capital E by N, which is equation 1. Let there be N0, N1, so on, NR are the oscillator, etc. are oscillators having energy 0, E, 2E, 3E, so on, RE respectively. Then N is equal to N0 plus N1, so on, NR. N is equal to N0 plus N1 plus N2, so on, NR. Therefore, N0 plus we are taken as 0 into N0. N1 plus we take E into N1, and N2 plus we taken as 2E into N2, so on. Then E is equal to 0 plus E into N1 plus 2E into N2 plus 3E into N3, so on, RE into NR, which is equation number 3. But according to Maxwell's distribution formula, NR is equal to what, ma? N0 into RE, N0 into E power minus RE by KT. That is Maxwell's distribution formula is there, ma. This every value we can take like that only. That above we are taken as total radiation of oscillators in the given enclosure. Here nr is equal to n naught into e power minus re by kt Maxwell distribution. Now each particle in the place of r 1, 2, 3 we can take. Then finally we are getting fifth equation. Substituting fifth in equation 2. What is equation 2? N is equal to n naught plus n1 so on. Therefore n is equal to n naught into substitute all these values means n naught common. Then we are getting 1 plus e power minus e by kt plus e power minus 2e by kt so on. Like that we can get e power minus re by kt so on. Now 1 plus e power minus e by kt plus e power minus e by kt whole square, like that. It is in the form of 1 plus x square plus x cube form. Then that 1 plus 1 by 1 minus x means 1 plus x square plus x cube so on form. Then it is n is equal to, we are taken in the place of x e power minus e by kt. Then this equation becomes n is equal to n naught by 1 minus e power minus e by kt, which is equation number 6. Now substitute equation 5 value in 3. Then e is equal to 0 plus epsilon n naught e power minus e by kt plus 2e into n naught e power minus 2e by kt plus 3e into n naught e power minus 3e by kt so on. Then e is equal to n naught into e power epsilon into e power minus e by kt, n naught into epsilon 2e power minus e by kt whole square so on we are taken. And now e is equal to n naught e into e power minus e by kt common. Then you are getting 1 plus 2e power minus e by kt plus 3e power minus e by kt whole square so on, like that we are taken. Then e is equal to n naught into epsilon e power minus e by kt 1 by 1 minus e power minus e by kt whole square. It is in the form of 1 plus 2x plus 3x square plus 4x cube is equal to 1 by 1 minus x square. In bracket, we can write in this form. Then this 6 and 7 values substitute in equation 1. What is equation 1? Average energy of Planck's oscillator E bar is equal to capital E by N. Capital E value you are getting from equation 7, N value you are getting from equation 6. Now substitute these two in equation 1. Then we are getting E bar is equal to N naught into E power epsilon into E power minus E by kt into that value is there, no ma? 1 by, in the place of E, you are writing this 7th equation. In the place of N, we are writing 6th equation. Then cancel N naught terms, remaining term. Then we are getting E epsilon E power minus E by kt by 1 minus E power minus E by kt. Then common the term in both the numerator and denominator. This one. E bar is equal to, this is over, no, all this. This one. E bar is equal to E into common the terms. Then finally we are getting equation 8th equation. E is equal to h nu by e power h nu by continuation of that one. This continuation. E bar is equal to h nu by e power h nu by kt minus 1, which is equation number 8. But we know that the number of oscillations per unit volume. The number of oscillations per unit volume in frequency range nu and nu plus dB is given by F is equal to 8 pi nu square by F is equal to 8 pi nu square by C cube into d nu, which is equation number 9. The total energy per unit volume belonging to range d nu is given by E nu d nu is equal to 8 pi nu square by c cube into d nu into h nu by e power h nu by kt minus 1 ma. Cancel all the terms. You are getting 8 pi h nu cube by c cube into d nu by e power h nu by kt minus 1. We know that nu is equal to c by lambda. Then differentiation of nu is equal to c by lambda square into d lambda. Substitute 11 in 10. Then we are getting E lambda d lambda is equal to 8 pi h by c cube. 8 pi h by c cube into c cube by lambda cube into 1 by e power hc by lambda kt minus 1 into c by lambda square into d lambda. 8 pi h by lambda power 5. 8 pi h by lambda power 5 into 1 by e power hc by lambda kt minus 1 into d lambda. That is Planck's radiation lemma. Very, very important. From that we are deriving Wien's law and Planck's law also there. Prepare seriously any 3 units. Okay. Planck's radiation law. After that, Wien's law from Planck's law also there. Rayleigh's law from Planck's law also there. Wien's law, how to get ma? First, we are taking Planck's radiation law. So Wien's law is valid for only shorter wavelengths. Wien's law is valid for shorter wavelengths. And hence lambda is very small. Where lambda is very small means e power hc by lambda kt greater than or equal to 1. As a result, one can be neglected in a comparison of, as a result, one can be neglected in comparison of e power hc by lambda kt for shorter wavelengths. Therefore, E lambda d lambda is equal to 8 pi hc by lambda power 5 into 1 by e power hc by lambda kt into d lambda. Then E lambda d lambda is equal to 8 pi hc by lambda power 5 into 1 by e power hc by lambda k to d lambda. Then cancel all the terms. We are getting E lambda d lambda is equal to a into lambda power minus 5 e power minus 3 by lambda t d lambda, which is Wien's displacement law. Like that only we are getting Rayleigh-Jeans law from Planck's law. These are the applications from Planck's law. Okay. So you concentrate Wien's displacement law, Planck's law, what is black body, and pyrometers, Armstrong pyroheliometer. So how to measure the solar constant, you concentrate this unit especially. Okay. Is there any doubt, ma'am? And I send no important questions. You prepare first to sort out what are the important questions in long and short. Repeated questions also, once you identify, concentrate that answers and the questions seriously in your textbook. And this what I shared to you notes in that. Okay, ma? Okay, now you have class, no? Shall I leave?